Hello everybody, my name is Connor Thompson. This is my Physics 2212 Lab 6 report. This lab is a magnet-based lab that requires us to observe and quantify Faraday's law by measuring the time it takes for a magnet to drop down an aluminum tube and comparing these measurements to one's model with below script code. We use the phone to time the magnetic data as the magnet drops, and then values of the aluminum tube are measured, such as its height, width, and mass. This lab primarily deals with concepts of Faraday's law, the Biot-Savart law, and Lenz's law. The magnet is the system and surroundings is the tube, and may be air resistance as it drops through the tube. The main results, besides the glow script code model, where the time to drop was about 0.34 seconds, the mass of the tube was 0.027 kilograms, the length of the tube was 0.35 meters, and the width of the tube walls were 0.012 meters, and the inner radius of the tube was 0.015 meters. These are the first results. This is just the glow script code with like the updated models, the updated values of the length, the width, inner radius, and such. This is the second half of the results. This was one section of the code. It couldn't fit in this previous slide, but this is the second half of the code, or the second third of the code. This was a video of the in-lab experiment right here. And then this right here is the generated model of the glow script code. You can see the magnet falling down the tube. It just stopped right here because the program ended, and this is the velocity versus time graph over time. The background of the experiment. Initial conditions, the magnet at the end was placed at the end of the tube, which itself is straight, and then it was hollow on the inside to make sure the magnet could fall through easily and not get stuck, with the north side of the magnet facing down as it fell through. Certain values of the aluminum tube are measured, such as width, length, and radius, and then the magnet is placed above the tube with the north side facing down. It is then dropped and recorded as it passed through the entire tube, with the time to entry and exit being recorded to determine how much the magnet is being slowed down the tube compared to like if we're just free falling in air. A program model is then developed to illustrate how the magnet would fall through the tube based on these given tube measurements in ideal conditions like without air resistance and with a perfect tube. We already went through these experiment results, but the assumptions and approximations we assume that the magnet would fall through with no air resistance, that the only force acting on the magnet were the ones instilled by its interaction with the aluminum tube that caused it to just slow down. What if the resistivity of the conductor were reduced as close as possible to zero? How did the dynamics of the falling magnet change? On account of Ohm's law, the current would have to increase to keep the voltage the same, and as such, there would end up being a stronger magnetic force that causes the magnet to fall slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If there were less material for the magnet to interact with and be slowed down by, whether it is slots or holes cut into the tube, it would ultimately fall down faster because there's less interactions by Lenz's law, the Biot-Savart law, all these things. And then assuming that these are representing glow script as well, we could also observe the magnet falling faster in the model. And that was the lab. Thank you very much for watching.